Welcome to the wonderful world of astronomy. This is part 4 of chapter 1. We're going to look at Spaceship Earth, and the idea here is we're going to look at how the Earth is moving through the universe. In ancient times, people believed that the Earth was the center of the universe, that it was just sitting still, and everything in space, the planets, the stars, whatever's out there, all orbited around the Earth. And the Earth was just sitting still. But now we realize that the Earth is moving. It has a variety of motions throughout the universe. How is the Earth moving through space? Contrary to our perception, we are not sitting still. We're moving with Earth in several ways and at surprisingly fast speeds. So first of all, we have the Earth's rotation. It rotates around its axis once every day, and this is actually the cause of days. We rotate around and we're either facing the sun, and that's during the daytime, or we're facing away from the sun, that's during the nighttime. Earth rotates from west to east, which means counterclockwise as viewed from above the North Pole. And we're rotating at different speeds. While the entire Earth is turning once per 24 hours, depending on your latitude, whether you're down at the equator or up at the North Pole, that would affect what speed in miles per hour you're moving. So if you were to be standing on the North Pole, right where this guy is, then you're not moving, you're just spinning around, so you're moving at 0 miles per hour. If you're down on the equator, then you're covering that largest distance, the circumference of the globe, right there in 24 hours. And so at the equator, you're moving at 1,040 miles per hour. And it's the same for a northern latitude and the same southern latitude. What I mean is this up here, so this is up in Canada. I'm going to guess that's about 50 degrees latitude, something like that. And this person's moving at 700 miles per hour. So let's assume that's 50 degrees north latitude. Then there's also people maybe at 50 degrees south latitude, and they're also moving at 700 miles per hour. So the farther away from the equator you are, the higher up in latitude, the slower you're moving. In Porterville, we're at about 35 degrees north latitude, so we are moving as we go around the Earth at 850 miles per hour as the Earth turns. Now, zooming out, Earth moves around the sun, Earth with the other planets going around in the solar system. So we say that Earth revolves, or it orbits the sun, once every year. And it does not move in a circle, it actually moves in an ellipse. Think of that as a circle that's been extended, it's been pulled out slightly, so an oval shape. It's called an ellipse. We are at an average distance of 93 million miles, roughly, which is 1 astronomical unit. You were introduced to that term in a previous video, Seeing into the Past. So that's the average distance between the Earth and the Sun. And it varies between about 91 million and 95 million, but on average, about 93 million. Earth's axis of rotation is tilted by 23.5 degrees, and I'll show you a picture of that on a later slide. And it points to a star called Polaris, or the North Star. It rotates in the same direction it orbits, counterclockwise as viewed from above the North Pole. So what that means, let's take the Earth going around counterclockwise, like my marker is going counterclockwise, and also it is rotating around on its axis in that same counterclockwise direction. And as we explore more the solar system, particularly when we get into chapter 7, you're going to see that there is a lot in the solar system that is moving around in that same common counterclockwise motion. The sun's rotation, the asteroids as they go around the sun, most major moons that go around their planets, and the rotations of most other planets. So that's something we will explore, that common motion that they have. This picture shows better the idea of the tilt of Earth's axis. So this oval right here, that's the ellipse as the Earth moves around the sun. And you see the North Pole, is always pointed in the same direction. It's tilted. It's not straight up and down. It is tilted at an angle of 23.5 degrees. And again, that North Pole represents the axis of Earth's rotation. This is a picture pointed at the North Star. The dot in the middle is the North Star. And for this camera to get this picture, the shutter was just left open for a few hours, gathering in all the light. And we see these star trails. So a star is seen to rise in the east and go across the sky and go to the west. And most stars rise in the east and go down in the west. And the other ones that don't rise or set, these are called circumpolar stars. And so, look at any one of these light trails that makes a circle. It's just going around, so it never goes below the horizon. But this is the view looking towards the north. As the Earth rotates, this is the motion that the stars make in the sky. Now, zooming out more beyond our solar system, our solar system is part of the larger Milky Way galaxy. So our sun and the things that go around it, including the Earth, orbits the galaxy every 230 million years. And so here we go, going around in 230 million years. Notice our location in the galaxy. Our solar system is about 27,000 light years from the center. The entire galaxy is 100,000 light years across, so we're about 2/3 of the way from the center. It says here, stars in the local solar neighborhood move randomly relative to one another at typical speeds of 70,000 kilometers per hour. It's not so random as that implies. When we get into chapter 19 on the galaxy, we'll look more at some of the order that actually is in those motions. Now, it is so slow. I mean, that's a very fast speed, 70,000 kilometers per hour, but it's such a large galaxy, we don't see that motion. We only see it over the course of many, many centuries, getting into thousands of years, that we would actually see the motions of stars. But for most practical purposes, the stars in the sky are in set positions. So we see constellations that people have known about for 2,000 years. For example, the constellation Orion is very well known and famous, and it is up there generally during the springtime. And next spring, it'll still be up there, all those stars, and the following spring, it'll still be up there. There are other stars that are up during the fall and during the summer, but those stars are regularly, for a given time of year, a given time of night, they are always there. As opposed to the planets, which are in our solar system, they are all over the place, and it differs from month to month what planets are going to be in the sky. So it says the galaxy's rotation carries us around the galactic center at about 800,000 kilometers per hour. So something over 500,000 miles per hour. Here is a painting of our galaxy. You see there's the central bulge and there is the disk, and then around it is the halo. It says most of the galaxy's light comes from stars and gas in the galactic disk and the central bulge. And again, we are about 2/3 of the way out from the center. So let me put my marker right about here. That's where our solar system is. But measurements suggest that most of the mass lies unseen in the spherical halo that surrounds the entire disk. So even though you can't see as much out here, measurements of galactic rotation and how gravity is pulling the galaxy around, there is much evidence that suggests that there is a lot of mass that's out here. And we can't see it, so that's what's referred to as dark matter. Continuing on, how do galaxies move within the universe? So we've talked about from local to zooming out. We've talked about the Earth moving around the sun moving around the galaxy. Now let's talk about the different galaxies. Galaxies are carried along with the expansion of the universe. So the entire universe is expanding, and you can picture it like a balloon. You take a balloon and imagine you can draw little dots on the balloon with a pen, and each of those dots represents a galaxy. And then you blow the balloon up, the balloon gets bigger and bigger, and the galaxies, those dots on the balloon, are moving farther apart. Well, that's what's going on with the universe, with space. Space is getting bigger, and the galaxies are moving farther apart. Now, often people will ask the question, where is the center of the universe where they're all moving apart from? Well, if you think, the answer is there is no center that they are moving apart from. And if you think back to the analogy of a balloon that's being blown up, if space is represented by the surface of the balloon, on the surface of the balloon, there is no one location that is a center. It's just the whole space is moving. Now, if you go into other dimensions, you realize a balloon is really three-dimensional, and there is that three-dimensional center of the balloon they're all moving away from. But that gets into, in our representation of the universe, that gets into multi-dimensions beyond our 4 dimensions of space and time. Edwin Hubble in the 1920s discovered that all galaxies outside our local group are moving away from us. He also discovered that the more distant the galaxy is from us, the faster it is racing away from us. And the conclusion is that we live in an expanding universe. So here's the idea. There was the moment of creation that we call the Big Bang, and the universe with all the galaxies, once they formed, has been expanding. And on this representation, kind of like my balloon that was being blown up, the galaxies are moving farther and farther apart from each other. And we will talk more about the expanding universe towards the end of the semester. So to recap this video, we are never just sitting still. Earth rotates around its axis once every day, carrying people in most parts of the world around the axis at more than, it says 1,000 kilometers per hour, so think of that, more than about 600 miles per hour. Earth orbits the sun once every year, moving at more than 100,000 kilometers per hour. So that's about a little more than 60,000 miles per hour. The solar system moves relative to nearby stars. The Milky Way galaxy rotates, carrying our sun around its center once every 230 million years. And our galaxy moves relative to others in the local group. We are traveling toward the Andromeda galaxy, for example, at about 300,000 kilometers per hour. And the universe is expanding. The more distant an object, the faster it moves away from us. And when we say an object, looking at the vast distances of the universe, we're talking about other galaxies. The most distant galaxies are receding from us at speeds close to the speed of light. So here it is, the entire summary of the various motions of Spaceship Earth. So what have we learned? How is Earth moving through space? It rotates on its axis once a day and orbits the sun at an average distance of 1 astronomical unit. Stars in the local neighborhood move randomly relative to one another and orbit the center of the Milky Way in about 230 million years. All galaxies beyond the local group are moving away from us with expansion of the universe. The more distant they are, the faster they're moving. Now, as we finish up chapter 1, this is a prelude to things to come in this class. How has the study of astronomy affected human history? Well, for one, the Copernican revolution, we'll talk about that in chapter 3, named after Nicholas Copernicus, showed that Earth was not the center of the universe. In chapter 4, we will look at how study of planetary motion led to Newton's laws of motion and gravity and gave us a better understanding of physics. Newton's laws laid the foundation of the Industrial Revolution, so we're able to take the laws of physics that he discovered and wrote down and apply it to industry and to make life better for us. Modern discoveries are continuing to expand our cosmic perspective. And that is the end of chapter 1. Have a great day.